Hey, so welcome to trigonometry. This is what 317 St. Patrick's Day. And so we're going to go ahead and we're going to review. Going to have some homework questions, hopefully, and review some of the things from chapter 5. Hopefully it'll be a good time. Anyways, wish you well throughout the day. It was a quick turnaround on the homework itself here. Let's see where you guys at, but primarily 5.5 was, do you have the correct formula? Can you plug it in correctly? That's essentially kind of what you had as far as homework is concerned. So any homework questions on 5.5? No, it was that easy. Or did some people not get started on it? No, okay.
Wait, can we actually go over 17?
Yeah.
17, absolutely.
We got it, but I was still
Oh,
like,
yeah. Wait, which is that your homework?
Yeah. Nice.
Okay.
falling on.
17, any others?
Oh,
Going
oh,
once,
oh.
going twice, just to get a list going. I assume we're gonna have a few more here. No, we're good, just 17? All right, well, let's jam with it here. So I got secant tangent inverse of x minus 2/2. There's what I got there. And we are gonna try to do what, everything in terms of x, is that right? Assume x is a positive integer here. Okay. Dun, dun, dun. Let me look at this really quick here. Dun, dun, dun. Dun, dun, dun. Dun, dun, dun. Okay. Tangent inverse. I'm gonna go to this right here. Here's my little rectangle. So this would be the sine value or the y value over the x value. I'm okay with that. What am I missing here for secant? Secant.
Just like plot.
Where's the cosine? Yeah, for hypotenuse. So I need hypotenuse here and then the x value here. I think that's good. Okay, let's go with it here. So Pythagorean theorem. H squared. That would be x squared plus, no, minus 4x plus 4. Are we okay there? Is that the way we're going with it? Yeah, okay. I got 8. So I have a square root of x squared minus 4x plus 8. And that has to be a positive. Talk to me. Are we good so far? Da da da. Okay, I'm okay with it, I believe here. So secant is going to be a hypotenuse on top. Over 2. Is that what the back of the book says? Let me check. Da, da, da.
Yeah, that was the.
Final answer, right, from the book? Okay. Everybody good there with 17? Okay, cool. Any other questions? Going once, going twice, before you have to turn it in today. No, still did not strike fear into anybody. Did you
Wait,
say?
you have to turn this in today? We've seen too much. We're too bad at war.
Okay, let's jam. This was a review day today here. Let's do this here. First of all, let's go to the challenge questions. Let's see, Wednesday. We're good. Any other thing from chapter 5? Any other thing that you guys have? That
Are
were
all the,
concept questions or anything? And
like,
then the study guide?
Formula's gonna be in the back of the book.
Yeah, let's see. So I'm gonna give you guys the printout like I usually do of this and this. The formulas that we've studied in chapter 5 are on this little section right here. The only thing that you're sort of missing in a sense is the Pythagorean theorem, all the different variations of the Pythagorean theorem for for tangent and secant, cotangent, cosecant. Those which, in a sense, hardly used anyway, sort of thing, you know. But you should know that you can vary those if you need to. Okay, we're good there. Does that make sense?
Wait.
Sure. So remember how we did these, the tangent, real quick here. Tangent, let's see, what is it? 1 plus tangent squared is equal to secant squared, right? So the stuff that we did in class compared to the stuff that's on here is just, when in class we did all the variations of that possibility, right? We solved it for 1, we moved the tangent over to the other side, right? We solved it for secant, so we have that. But besides that, everything is here. In fact, it even labels for you. It's like 5.1, 5.2, and it goes on. And the sum to product formulas, the stuff we covered in 5.5 is right here and right here. So we have all of the different pieces. So yeah, technically you should have all of them. Okay, with that, dun, 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 dun. Okay. Test is set for, today's Wednesday, technically it's set for Monday. Let's vote. Anybody want to do it Friday?
No.
Okay. Let's go with Monday here. So I'll think of some fun stuff to do for Friday here. Let's jam to this first though. The challenge questions. Let's do those first, then we've got some other things. So calculate the exact sine value of 15 degrees using the difference formula. So anybody know the difference formula? Then we're going to use the half angle formula, and we'll see what they look like. Let me start off that problem. So that's a fun problem to sort of think through and see what you can make out of it here. You use a calculator to make sure they have the same value and then prove it. So let's start that one. Okay, the other one is derive the, remember how we did it on the board over here? We derived the sum formula for sine using this little diagram. Well, it's kind of funny, in trigonometry, you can start at any which way. You don't have to start with the sum for sine and then move your way across. You can start at cosine, just based upon the difference of the diagram. And so you start off with cosine, you base that as the sort of your basic formula, and then you build the other ones off of it either. Kind of fun. And then the toughie of the challenge problems is this one right here. And so can you spot somewhere over here the difference formula for sine? It's just nicely sitting there like, oh, that is so cinchy. And just like, you write it down and you're like, cool, done. Good? So, but you have to spot it. It's kind of like one of those visual things that you sort of see it here. Okay, I'll leave that here, but this one right here, I do want to get to. It is the easier one of the three, and it's kind of interesting to sort of see. So let's kind of jam with this one here for a little bit. Okay, so I need the difference formula for sine, and then we're going to use the half angle formula for sine. So let's jump to this here. So I need half the class. Corinna, I may as row. I need you guys to find sine of 15 degrees by the difference formula. You know what? I should be better with my handwriting here. By the difference formula for sine, obviously. Cool. George's row, there's only 2 people there, and Grant's row, even though you don't own the row, but.
Yeah.
The 3 of us do that.
Yeah.
You had to specify our rows, but we do own our rows.
Yeah. That's funny. Just joking with you guys. Let's see. Can you guys get sine of 15 degrees?
Yeah, I did these a little while ago because I didn't realize we'd be going over them.
By the half angle formula. You guys do it by the half angle formula. So yes, you got to look it up. You got to do that. Yeah, got to get out them books or get out your notes. I'll give you guys just a quick little minute or two. Some people can rest if they did it already. All right, first two rows, people. Which two angles did you guys use or subtract from to get 15 degrees? Just so it could be similar.
I did 30 minus 15, but now that I'm thinking about it, I should have done 45 minus 30. So let's
Yeah,
go 45 minus 30.
Perfect, yeah, 45. So the angles that we know already before we started chapter 5 would be 45 and 30-degree angle. This is the difference formula because guys are doing it this way. So I think it's sine, cosine, is that right? Minus cosine, sine, I believe. Is that what we have there? Cool, and easy enough to get here. Let's see, that's going to be root 2 over 2. Talk to me here, cosine 30.
The cosine and the sine on the second part are
Oh, yep, sorry. Yeah, this should have been 45 first, 30 afterwards, right? Boom, boom, boom. Good there. All right, cosine of 30 degrees. Dun, 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 dun. Square root of 3 over 2. I agree with that. Minus cosine of 45. I like 45 degrees because it's always going to give you square root of 2 over 2. Sine of 30 has to be the other way around. So if cosine is root 3 over 2, sine has to be 1/2. Multiply these guys together. Voila, over 4. Voila, over 4. And I guess I should write it down here. Final answer, square root of 6. Subtract square root of 2. All that divided by 4. Are we good? I don't know. First two rows, are we good? Yes, okay. We get the nod. Okay, the other one here, the half angle formula. Anybody give me the half angle formula? I don't know.
It's root 1 minus cosine 30. That's over 2.
Gotcha. Perfect. Okay.
Square root the whole thing.
I think it's written like this, right, Grant?
Yeah.
Theta divided by 2. And since we're in quadrant 1, I could already use the positive 1. And I always forget plus or minus? Minus for cosine and 2. Awesome. Okay, let's plug it in. This would be, technically it's 30 divided by 2, which is 15. Cosine of 30 divided by 2. And we have this little fun little process that we do, right? Cool. Help me out just a bit here. Cosine 30 degrees. Root 3 over 2. Okay. Common denominators would be 2 over 2. Hey. Bless you. It disappeared on me. Mm-mm. Okay. That was weird. Let me go back over here. Let's see. We're right there. All right. Too much trigonometry for PowerPoint. That's what it is. Not for us, just for Microsoft. That's all. So I got this right here. And let's see, I'm going to make a little 1 underneath the 2 and multiply it through by a 1/2. And I got myself 2 minus root 3 over 4. Almost there. I'm running out of space here. Let me make this a little smaller here. So it's the square root of 2 minus root 3 over 4. And eventually, all the way in the back corner over here, we have ourselves a square root of 2 minus root 3 over 2. Boom, are we good? So hold on though. This is sine of 15 degrees. That's sine of 15 degrees. That's true. Then this little piece right here, ding, 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 should be the same thing as this little piece right here. True or false? What do you guys say? I say true. Okay. So then let's do this here. Let's jump on the calculator real quickly here. And anybody from rows 1 and 2, can you guys punch this into a calculator? Give me a decimal approximation, like to the near, like 4 decimal places or something. I want to see if these guys are the same or not. So 0.2588 and blah, 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 right? Actually, no, let's all of us do this here. So Grant, which one did you do? The difference or the?
I did the difference.
The difference, okay. So Grant did this one. And you guys punch it in 0.2588, and then the rest is over here somewhere, right? Okay, Grant, can you punch in the square root of 2 minus square root of 3? All of that divide by 2. This one's maybe a little tough one to plug in. And let me try it myself as well. My mouse seems to be not cooperating with me today. Why is that? Why you not be nice to me? Okay. So you guys, real quick here, verify, because it needs to be verified. Verify, in fact, you get the same exact answer for both. 0.2588, blah, blah, blah. Cool, okay. Those checking here. Got about 3 more people punching in the digits here. Go for it.
I got 2, 5, 4, 3, 7.
Ooh, slightly different, huh? But which one? For the first one or the second one?
First one.
First one, okay. And so let's make sure that we got it here because this is part of our proof. You should get an extra parenthesis in front. And when you punch in the square, it's going to open up a parenthesis. So close off this parenthesis, minus, open up another square root is going to open up another parenthesis, close off this one, and then close off the
I didn't
top.
put those parentheses inside, but I was able to separate.
And then put divide by 4.
Oh, wait, I see that. Yeah, I got the same thing that Grant did, so, yeah.
Okay.
That's what I did.
Cool. Okay. Just want to make sure, yeah, the people that are verifying it to make sure you guys got it. We good? Agreed, agreed. Everybody agreed? Okay. So that means, according to this right here, we have ourselves a, oh, you know what, like we did, this is not good. You know what? Let me check. Maybe, let me check something on my mouse here. There it is. Now my mouse likes me. Okay. So remember how we used to do identities? We proved that this side is the same thing as this side, right? So we do have to do the same thing here. So the square root of 6, subtract the square root of 4, at least calculator wise, it says this is true. Boom. Strangest thing. So I guess challenge problem number one is this right here, is the fact that can you prove that this is an identity? Can you prove that those two are actually the same thing? All right, that's challenge problem number one. We good? Does that help out?
Wait, so we just did that, right?
Well, let's see. We did it by the difference formula. We did it by the half angle formula. We found out that we found the values of them, right? And then we verified by calculator that they are the same because it gets the same decimal approximation. So now what we have to do is we have to prove it. Prove that that is the same thing as that.
Yeah, how do you do that? What we just did. Yeah.
Oh, I got it. Okay, yeah. So, sure. Let's see if this makes sense here. You know how identities, we have to prove one side is exactly the same thing as the other? Right? And that proves the fact that it's the same. Like eventually you get to tangent is equal to tangent. You're like, yes, awesome, we got it, right? And so what this one is, we have one set of a way we can find sine of 15 degrees. And throughout the chapter, we figure out another way to find sine of 15 degrees. We know those have to be the same, right? Because they're the same value, there's the same angle value. But when you do the work for them, they turn out to look different. That's the issue. They look different. The calculator says they're still the same, but analytically, can we prove the fact that that side is the same as that side? So we got to do the same thing that we did with trig functions here. Eventually, you're going to have to get something here that's exactly the same looking as something here.
So we just don't trust the calculator?
We do, yeah, we do. But it's the same thing as, let's say, we do trust the calculator. But it's not proof though, because first of all, we do stuff to verify things, like even in graphs. Remember how we did the graphs of like cosine? And then we did the graphs for sine. And then we said, you know what? If we just scoot sine this much right here, that will look just like cosine. So if we say take sine and we say x minus pi over 2, that will, or plus pi over 2, that will scoot this over here. So now, graphically, it looks just like the cosine curve. But then what we did is we say, okay, if that's true, then what we're going to do is we're going to prove it. We're going to prove that this is actually, in fact, equal to this. Because a graph doesn't prove anything. Does that make sense? Not analytically, not in a math sort of way, not in a like for sure. Okay, we good? So then if we do this, we say to ourselves, okay, hold on, that is the sum formula for sine, isn't it? See if this makes sense. This would be sine of x cosine pi over 2 plus sine of pi over 2 times cosine. See if this makes sense, guys. Talk to me here. We have that on our hands. Anybody cosine of pi over 2? Not pi over 4.
Oh, wait, 0.
0. This would be cosine of x, and then I need sine of pi over 2. 1, That becomes 0. That becomes cosine of x. That becomes cosine of x, and now we have this right here. So what's the difference between looking at it on a graph and saying, hey, if we just scoot it over to the right a little bit by pi over 2, it looks like cosine, as opposed to, oh, went the wrong way, as opposed to this right here. I don't know, Mr. G, what is it? So the graph technically doesn't prove it, not in a mathematical sense. This right here now proves it in a mathematical sense. You've got equal signs that turned into other equal signs that turned into other equal signs, and now both sides are equal. We good? That's We call it an analytical proof. Beyond shadow of a doubt, that's it. So can we, for a challenge problem here, can we analytically prove those two to be the same? That's the question on the challenge question. We good?
Wait, so
Yeah, all I'm hearing is you don't trust the calculator.
I see how you worked through it when there was like the sine and the cosine there.
Yeah.
Because they plug into formulas, but this, I don't know what I would do from here.
Shucks-a-roo.
You do just numbers, you can
I
just
know.
reduce the numbers, and then the numbers will be the same if they are the same,
Using a
right?
calculator.
Using a
But like,
calculator.
these are already the simplest that they can
Yeah,
be.
yeah, I can't see it.
So you need to make one less simple.
No,
That's
don't do
the
that.
key.
Yeah, key is how do you mess with that? Because we've never messed with that before. We always did trig functions that had identities with them. And I'm gonna stop there. We're good. It's a total teaser, that's all. Okay. That's number one. Jump to number two, just to start off the challenge questions. Number two, you probably should look back at how we did. So this is challenge problem number two. In case you try it. If you choose, what is mission possible? If you choose to accept it, this will self-destruct in, nah, it won't self-destruct. Okay, 5.1. And from your notes, you can actually go back to your notes if you wanted to, or you can go back to the textbook here on page 266. That's when we set up the little formula or the diagram. Keep that. Let me jam to, what did I want to do? How did it go to? Yep, this one right here. Notice we did, what did we do in our notes? We derived the sum formula for cosine. That's what we did in our notes. Eventually we got something that looked like this here. We got cosine of A plus B from the diagram itself. Cosine of A, cosine of B minus sine A, sine B. We good? We did it on the wall. Remember that? When most of the people were confused? Remember that one? That was that Monday. Okay. But we got everything from this diagram. If we think about these little triangles right here, so this is A, this is part A right here, this is triangle A. And if you think of adding B to it, it makes, instead of that triangle, now it makes this triangle right here. Here's your triangle A plus B. If you subtract B from A, it still makes the same angle. So let me draw this in a different pen. It makes this angle right here. And these two angles are technically congruent to each other, is that right? Because they technically have the same angle. This is an angle of A plus B. This is an angle of A plus B. And the sides are all the same. Sides are all 1 unit away from each other. That's how we did that one. And then we found out that if two triangles are congruent, here's a little tricky part. We know that the hypotenuses are the same as well. We're good. So the question is, how do you find the hypotenuse? And then the question is, which one do you want? So for this piece right here, we had to set it up. So I'm going to just kind of let that, just start you guys off that way. So that's the way we start off for cosine of A plus B. We looked at the hypotenuse here. We looked at the hypotenuse here. And we said to ourselves, that should be all the same as well, or the distance formula between those two. And we started setting it up. So the math behind it is not that difficult. It's just a matter of lining up which ones you want. We're good for the challenge problems here. So I'm going to let you guys just take a look at page 266 if you want to start on that one. Okay. And challenge problem number 3. Well, the diagram is given, and it's one of those that you look at it, and you're like, boom, it just kind of like jumps out at you, like, oh, that's what it is. And then you go for it. And then there's some right triangles there. Got to keep where the right triangles are, and you go from there. So I'm going to stop there. We're good as far as challenge problems are concerned. So for honor students, you guys have to do at least one. We good? Canon students, you can do it for extra credit. We're good. You don't need to complete one. Not to like really tweak your brains for it. Okay, stop there for those guys. Enough of an intro for the challenge problems, I think. What do you guys say?
Third one, I just cannot figure out.
I know it's one of those. It's in mathematics. Did I tell you the story about my theory class of mathematics? So we get into class, the instructor says, hey, in this class, all semester long, you just have to solve 4 problems for the A. That's it. For the B, you gotta solve 3. For the C, you solve 2. D is 1, and then if you can't solve any, you get an F in the class. You're done. That was it. That's your grade in the class. And so he gave us, every single month, he gave us a slew of problems from a math journal. It was undergraduate mathematics journal. So we get it for, at the beginning of the month, we get it. And you can try any problem there. There's about maybe 30 problems, maybe 15 problems in each journal. And it says just solve 1. And you had to solve 1 a month. And you had a group of 3 of us, or maybe 4 of us. I think there's 3 of us in a group. And you just grappled with the problem all month long. And he would kind of give you, and during lecture, we would talk about different types of different types of theoretical math problems. How do you solve them? What are some techniques and all that stuff? And then that's the way you went. That was your class. Have fun. And so what usually happened is you look at something, you go to sleep, you come back 3 days later, look at it again, go to sleep again, think about it some more, and then all of a sudden on Thursday afternoon, it's like, oh, dude, this is so awesome. And then you start writing down a whole bunch of stuff because now it actually made sense. And so this is one of those. We good, Amaya?
Yeah.
Okay, I'll leave it at there at that point. So it's the difference formula for sine. So try to at least figure out what would be the difference formula. How would sine come into this here? And so how does the other piece work? And so it's a visual problem in that sense. It's also a proof. Sometimes in mathematics, we have visual proofs for things. So the Pythagorean Theorem, there's like 34 different proofs for the Pythagorean Theorem. Several of them are just a picture. So here's your picture, boom. And it's like, oh yeah, that's the proof for it. In fact, President Garfield has an original proof of the Pythagorean Theorem, and it's just a picture. Here it is. Okay, back to stuff for the class. Let's see, we have 15 more minutes remaining. Let's do this here. Study guide to the test itself. I should bring that up. Test number 5, study guide.
On Friday, can we just do like a bunch of reviews all together?
That's what I was thinking as well here.
Just a little more.
Zoom in, yeah. Let me see if I can get rid of this because I don't need that. And then, does that help, Grace?
Perfect.
Okay. Prove each of the following identities are true. Prove that each of the following identities are not. Let's see. Prove that each of the following statements is not an identity by finding a counterexample. We good? So I figured let's do maybe even like do a practice test on Friday. Would that work? I'll see if I can send it out earlier just so you guys have it. And then we can go. Let's do this here. I'll send out a practice test sometime tomorrow-ish. If you want to at least take a look at it. Huh?
So before, or you saying we're taking practice test in class?
I want you to see it before class, just so you can see it, and then just work it out during class. So we'll kind of use Friday for that. Cool. As opposed to me handing it Friday and then let's go, without you guys sort of like at least wrestling with it a little bit here. Okay, we're good. And so for the remaining time, let's do this here. Let's do first two maybe. Prove the following is an identity. So 5.1, let's start. It would be like a practice test to start off with here. 5.1, like the number one piece to it here. Well, what do you know? There's a start of it sort of thing. So prove. I can do that one here. Let's see. I like that. Let's do the prove that this is not an identity. So prove this is not an identity by finding a counter example. And so I would have plus that. So we know that sine squared theta plus cosine squared theta is equal to 1. We know that for sure. But sine squared plus cosine squared, does that equal 1 as well? Got the squaring part to it. So this is 5.1. This is this whole concept of just identities. Okay, this is, at least we know this. This is an easy one. Prove, we know it's not an identity, right? So you guys just give me an angle, any kind of angle that works so that it is not true. Because some angles will actually make it correct. Notice if I use pi over 2, or theta, we should say theta. So use theta is equal to pi over 2. Is that true? Let's check it out. If we plug in sine of pi over 2, cosine of pi over 2 is equal to 1. That gets me sine of pi over 2 is 1. Cosine of pi over 2 is 0. Hey, so it is an identity, correct? It's kind of like a broken watch is right twice a day.
Yeah, so that would be finding the counterexample that makes it work.
So this is a counterexample that does not work well for what we want to do. It actually proved it. Like, oh no, that's not good. Yeah, we're trying to prove that it doesn't work. Because this little piece says it works all the time, right? If you say, hey, sine theta plus cosine theta equals 1, the assumption is it works all the time. This is an identity. Yeah, it has to work for all. So the broken watch is correct twice a day, but it's not a working watch. So then for the test itself, you're going to have to say, I'm going to use theta is equal to pi over 4. That one right there is going to prove that this is not true. Because when I plug in sine of pi over 4 plus cosine of pi over 4 is equal to 1. This is root 2 over 2 plus this is root 2 over 2. And this is going to be 2 root 2 over 2. The 2's cancel, and I'm left with this, which is not true. So boom, I proved with one counterexample the fact that is not an identity. That does not work all the time. Okay, and this was what? This was the beginning. This is 5.1. This is our basic identities that we had. And we are, we're proving basic identities. We're proving basic, come on. What's it called here? Yeah, basic identities in order to prove certain things are true. Okay, we're good there. There's one that makes sense now, as far as proving something, not an identity here. Let's jam to number 2, time remaining here. So now prove this is an identity. And that would be secant theta minus cosine theta is equal to tangent theta multiplied by sine theta. It's all yours. Let's see, I'm gonna start off, got 2 minutes left here. I'm gonna start off with any side. It doesn't really matter here. Maybe this would be 1 over cosine theta. This is cosine theta. Okay, so let me kind of think about that for a little bit here. Let me actually do this one. Maybe this was easier. Tangent is sine theta over cosine. Okay, I see my denominators might be happening here. This is sine theta over 1. Oh, you know what? This side is simple to simplify here. So I'm going to go for this right here. Somehow I got to get sine theta squared, sine squared theta over cosine. At least that's the goal. That's the most simplest form. And I think I know which way I'm going to go. I'm going to make this into a 1, and then I'm going to have to get common denominators here. So cosine theta right there. Then I have cosine theta in the bottom. This will be 1 minus cosine squared theta. That's perfect. And then I have what I want. I have proved that these two are an identity, which means any angle I plug in, it doesn't matter what angle it is, could be 45 degrees, 30 degrees, 25 degrees, 68 degrees. If I plug in secant of that degree minus cosine of that degree, it's always going to be true of tangent of that degree times sine of that degree. Okay, we good? Right. So in light of St. Patrick's Day, I'll let you guys out 30 seconds earlier.